Well, thanks, Pavel and Derek, for the invitation to talk at this event, and also for being flexible with the times, because as Pavel mentioned, I'm maybe 6 hours or so ahead of you guys, so it's better than doing it at 3 in the morning or what it would usually be. So yeah, let me just share my presentation. See the slides, right, Pavel?
Yeah, all good. Yeah.
Okay, cool, awesome. So yeah, I'm going to talk about this model that we base a lot of our natural language understanding on, which is called ConverT, which is standing for Conversational Representations from Transformers. So what I'm going to talk about is basically covered by these papers. And hopefully I can share the slides so you can look at those if you're interested. But basically these are 4 papers. The first one is the pre-trained model that a lot of this is based on. The second one is the data set, which is English language conversational data set. And then the next 2 are the 2 NLU applications, which I'll try to focus on. So we're talking about intent detection and value extraction. So if you know Pavel, you maybe know a bit about PolyAI already. As he mentioned, so I was in the dialogue systems group in Cambridge. Pavel was also at that group, and the 3 co-founders of the company were as well. So that's a kind of academic background, I guess. And what we're doing now is commercializing dialogue systems. So we're building automated voice agents for customer service broadly, for use in automating call centers. And that's for multiple different applications, things like restaurant booking, troubleshooting your internet, online banking help, and all sorts of things like that. But basically it's task-based voice chatbots. Okay, so when we're developing these task-based systems, there's a few things that all kind of need to line up. The first is to find a convincing application, something that actually solves a problem that people have. And that also ties into sort of being a commercially valid problem to pursue, and something that is possible given our current technology. It doesn't require, really amazing level, like human levels of language understanding. It's something that we can tackle. The second is that we need a way to do meaningful evaluation so that we can measure our progress towards the goal of having a system that is getting closer to human level natural language understanding. And then the last thing is basically about whether or not this is machine learnable. So we have the evaluation, but can we gather annotated data as part of the feedback loop to improve our models? So if we have a system, if we have all those things lining up, then we can kind of get a baseline system running, have it talk to real users in a call center, start to label the data from those conversations, and use that data to update our machine learning models and come up with an improved system. This could also be doing things like A/B testing, so trying 2 different systems and picking the best one. But a lot of this hinges on having that baseline system to start with. And really, the question a lot of the times for us is, how do we get a baseline system, a baseline dialogue system that's good enough for people to talk to, so that we can start to iterate on it. And by the way, as I give this talk, please feel free to interrupt and ask any questions, anything that's not clear. Cool. Building this baseline system is particularly hard as you think about scaling up a company, I suppose. So we're interested in scaling across multiple languages, multiple domains, and different features in each domain. And for each one of those, we need NLU models. So we need to train intent classifiers, we need to train slot value recognizers. We might need to train certain aspects of the response selection or generation, perhaps. So how are we able to minimize our reliance on annotated data? Like, does each of those models need thousands or tens of thousands of examples? Or, can we make it so that we'll need a handful of examples to start launching a baseline system? And in general, how can we scale better? So I guess this is, how can we get away with less data so that we can scale across skills and domains and languages? And the answer that I'm trying to sell here, I suppose, is we can do natural language understanding that scales better by using large pre-trained models. And particularly since we're doing conversational applications of NLU, those models should encapsulate some knowledge of conversational response. And this idea of pre-training in NLP is not new, and it's obviously gaining a lot of traction recently. So, things like taking a pre-trained BERT model and fine-tuning it on a certain tasks. Those would be pre-trained language models. So those use unlabeled text and some kind of unsupervised objective. And those would learn general representations that are good for text or words in a context. And what I'm going to talk about now is about how we can pre-train a model, not just on general text, on a language modeling task, but on conversational data. And the conversational data that we're using at PolyAI is shared in a GitHub repo, which is on this slide here. The main one is Reddit, which is comprised of 3.7 billion comments, and that's growing every month. And from that, with some filtering and extraction of conversational examples, we can get something like 727 million conversational examples, mostly in English. And there's another couple data sets that we share in that repo, Open Subtitles, which is from movies and TV shows, and then Amazon QA, which is grounded in specific products. So it's question answering for specific products. And the scene for conversational data sets, we're basically trading off the size of the data with the amount of annotation that the data has. So you can see multi-was, for example, is something that Pavel worked on, is large for a fully labeled data set. But if you're thinking of training on this Reddit data I'm talking about, which is the last row, that doesn't have the strict annotation of intents and slots and values, but we're talking about billions of turns or billions of examples. And the task that we train the models on, the pre-training task, is a bit different to the typical language modeling task. So just to recap, a language modeling task is predicting the next word given a prefix of words in a sentence. And there's also masked word prediction, which is like the BERT pre-training objective, where you'd have a sentence and you would mask, you could delete some of the words and ask, what is this masked word in the middle? And the conversational task that we'll look at is response selection. So since we've got conversational data, that we are proposing a conversational task. So this response selection task is given a sentence or given a message that happened in the data. Can the model predict the true next sentence that we saw in the data versus some other competitors? So we just do randomly selected other responses. So here, given any recommendations for short trips from Singapore, the model should realize that this response about ferry trips to Bintan is more appropriate than the other candidate responses. So just a sort of side-by-side comparing this response selection task with the language modeling task, the first difference is the type of data that we use. So instead of using large text data, we're using large conversational data sets, in particular Reddit. The second thing is that we would expect a model trained on response selection would learn representations that encode conversational cues, whereas a language modeling task would encourage the model to learn representations that encode just the next word cue or surrounding word contextual cues. If a response selection model will be trained to encode a full sentence or a full message that a user might say, whereas a language model, like a BERT type model, is more about encoding individual words contextually. And lastly, the response selection task is actually already useful for building things like chatbots, because if we have a model that is good at selecting responses, we can just immediately use it to pick a response given a candidate. However we got the list of candidates, we could use a response selection model to decide what to say next in a dialogue. Language model is not so directly applicable as is to dialogue systems, but it might be useful for generating responses or even just scoring responses for fluency or for appropriateness. Okay, I think one of the big insights here is that we think that neural techniques are really basically good at being feature extractors. They're good at finding embeddings of things like natural language. So the overall picture is that we're going to learn a model on the large conversational data on this response selection pre-training task, and then we're going to apply it to intent detection and apply it to value extraction by putting small models on top of that big pre-trained model. So now I'm going to talk about the actual model architecture that we use for response selection. Now this is called something like a dual encoder dot product model. So it was originally applied to Smart Reply on Gmail Smart Reply when I was working at Google. And you also might be familiar with the universal sentence encoder, which is my old team at Google. It's a very similar approach to those models. But the high level idea is that we're going to train two side-by-side subnetworks. One that encodes the input dialog context to a vector, and the other which encodes candidate responses to another vector. And we're going to train the model such that it gives a high score, which is computed as a dot product between those vectors. It'll give a high score to input response pairs that we find in the data, and a low score to random pairs that are not necessarily in the data. So when we're training, we'll have a batch of n input sentences and n responses, such that each one is paired, and we can, since it's a dot product, it allows us to do efficient training using all the other examples as negatives. So here, imagine that we've encoded the input vectors x1, x2 up to xn, and the response vectors y1, y2 up to yn. Then this matrix here, which is the matrix of all possible scores of every input with every response, is a very efficient, matrix outer multiply away from computing the vectors in the first place. So in training, we will learn a softmax over the rows. So that will encourage us to give a high score along the diagonals and a low score in the off diagonals. And we're effectively getting n-1 negatives for every
Sorry. What in the case when you have two questions with exactly the same meaning, but with a different input vector? Though the score.
Yeah, this is kind of this is doesn't take into account that case where there are two questions that kind of conflict with each other, and it also doesn't take into account the situation where there are two responses that conflict with each other. But the hope is that by training on a large corpus like Reddit and taking random batches, that kind of noise balances itself out.
Okay.
Yeah, but it would be a problem if you had a small data set where you had multiple good answers for each input. But it's sort of just any pre-training task that will teach the model something about the mapping between input and response. Okay, so here's just a picture of it mathematically in case it makes more sense to anybody. We are learning the network basically consists of two subnetworks, F and G. F encodes the input to vector X, and G encodes the candidate responses to vectors Y. And then the score of Xi with Yj is just a dot product of those two vectors. And then we'll learn a softmax score, a softmax loss to encourage the diagonals to be high, and this I call it dot product loss. Okay. So as well as this efficient training, it also means that we can pre-compute response vectors in an application where we're doing response selection or response scoring. So if we have a new sentence come in from the user, all we have to do is encode it as an input X. And then if we have a bunch of fixed candidate responses, all their vectors Y can be pre-computed. So this is the case for Gmail Smart Reply, for example. We've got like tens of thousands of candidate responses, but we don't need to compute those every time. And then to find the top scoring responses, we can do an efficient approximate nearest neighbors search to find the best responses. Cool. So yeah, this is just a sort of computational complexity of what I was just saying.
Hey Matt, a quick question on this dot product choice. Yeah. If my understanding is correct, that would work well when we are trying to find like two sentences that are similar to each other, so they are encoded in a similar way, right? And then the dot product should be large. Now, with question and answer, I would imagine that sometimes they are not similar but complementary. So what's your intuition why this works actually in your case?
Well, actually, it's not necessarily a similarity metric because these two functions F and G are different functions, right? So we are encoding the input through a different network than we're encoding the response. And that way, you're actually able to model any kind of data if your vectors are big enough.
Makes
sense.
So
it's not actually similarity. It can learn an arbitrary mapping from input to response. Does that make sense?
Yep. Thank you. Helpful.
Nice. Okay. And the metric that we look at when we're training response selection models is this 1 of 100 accuracy, which is how often the correct response is ranked versus 99 random ones. Okay, and here's the actual model architecture. So I just talked about it as F and G, but actually we're using a bunch of shared transformer style blocks. Input and response are both put through these 6 transformer style networks. These are slightly optimized versus BERT, for example. We don't find any improvement from using multi-head attention, for example, and we're using lower dimensionality. And all the details would be in the paper on this. But so after the shared transformer layers, we then do 2 different feed-forward networks, resulting in this 512-dimensional vector. Does that make sense? And when we look at the 1 of 100 accuracy for different approaches, we're able, we show that the ConverT model is competitive. And since then, we've got a few more fair baselines, I would say. DSTC8, for example, had, was it 8 or 7? 7, I think, had Reddit response selection as one of the tasks, and ConverT was beating the other models on that evaluation as well.
Can you maybe explain what you mean by DSTC for people into conversational AI field?
Yeah, DSTC is now the Dialogue Systems Technology Challenge. So it's a series of research challenges that runs every year, and they will pick different tasks in conversational AI. So when I was referring to there, they took a subset of Reddit, and they were basically doing 1 of 100 accuracy. We didn't compete in that challenge, but we presented results on it after it happened. Cool. And this is kind of just a note on how we ran the optimization process as a kind of machine learning team. Kind of the main thing that we did was to fix the length of time that we're training the model. So we say, if your model gets, we'll measure your model based on the 1 of 100 accuracy it gets after running for 18 hours on 12 GPUs, which is kind of arbitrary. But what it did was it forced us to make sure that the model was running efficiently. And in the end, we got a model that was actually about 40 megabytes in size and cheap to train, and actually runs fine on a CPU, which is super useful for our deployments. And here's a picture of the progress that we had over like particularly productive 3 weeks over a year ago now, optimizing for that 1 of 100 accuracy. A lot of the big improvements were switching to the transformer style architecture versus doing a kind of bag of words, unigrams and bigrams type model. Various other improvements, including using quantized training, so that we're training using float 16 precision. And that just allows us to train on bigger batches. And for this model, bigger batches means more negatives, so better training signal. Cool. So that is the ConverT model. So it's a response selection model that encodes sentences into fixed dimensional vectors. And it's trained with conversational tasks in mind. So next I'm going to talk about the specific conversational tasks that we apply those representations to. The first task is intent classification. So what's intent classification? I suppose if you were at the talk that Rasa gave, you'd know about this. It's basically classifying the user's message into categories that are useful for deciding what the system ought to say next. So for example, in a restaurant booking system, you might have an initiate booking intent, a cancel booking intent, and restart intent might be a sort of globally useful intent to have. So basically, we need to find a way to classify into one of n categories. And in particular, we're interested in a data efficient way so that it scales well. And the way that we use the ConverT model is to basically draw a line above the shared transformer layers. So this will give us a 1024 dimensional vector trained on the response selection task. And then we just add a couple feed forward layers on top of that and train a one of n categorical classifier to output intent probabilities.
Hey Matt, let me check my understanding. So going back to the previous, like when you share the model, there are two functions for encoding. One is for encoding the question, and another one for encoding the response. Which function are you using here for the intent classification?
Sure. So since those two blocks are shared, it could be either one, but we're cutting it off at the two-headed self-attention stage. So the dimensionality of the vector of the model is basically 512 all the way up, and then these two heads concatenated give us 1024. So it's a representation that's not geared particularly towards input or response, but it's actually shared by the two subnetworks. Yep. And we find that works best. You could also try using the top of either of those two towers, but it doesn't work as well for whatever reason. Yeah. Okay.
Yep.
So yeah, so we're taking just above the attention reduction. So we've got two attention heads and then concatenate those vectors. And now we've got a small NLP on top. And since the ConverT model is pre-trained on, all of Reddit, it's already putting vectors into a meaningful clusters, we find. So if you look at the data, actually something as simple as a linear classifier or a nearest neighbors type search works almost as well as training an MLP on top. And so I guess the key point is that if you've got already good representations that can come from pre-training, then small model on top will it can be very small because you've got almost all the way there with the big model. And so here's an evaluation comparing basically comparing BERT to ConverT. And this is to try to show that the main difference is that BERT is trained on language model or masked language model word prediction, and ConverT is trained on response selection. There's more details in that paper mentioned there, but ConverT does better than BERT on these different data sets, and it's particularly better for the low data setting. So the 10-30 full conditions, those are different amounts of data. So training with 10% of the data, 30% of the data, and all of the data. So overall, we find that you only really need a handful of examples of an intent if you're with this approach. And that allows us to build these baseline systems quickly. Yeah. Oh, we got a text question. Okay. Should I read it? When saying training NLP on top, what exactly do you mean by NLP? So here I'm talking specifically about the language understanding that we need to do in a dialogue system in order to know how to respond to them. So the first thing I was addressing is intent classification.
Sorry, but this NLP for you, it's a model. It's a small model for something. Oh yeah,
in this case, it's a small model.
Thanks. Yeah. Okay, yeah. Thank you. I'll explain.
Yeah. And then there's another type of model I'm going to talk about now, which is not a classification model, but is a value extraction model. Because as well as detecting these intents, we also need to extract information from the text that the user said. And this probably has a lot of different names, like slot filling. I'll refer to it as value extraction. In a dialogue system for restaurant reservation, we might want to extract people's names. So like Henderson would be a name here, but for example, Harry is not a name we're interested in. That's actually the name of the bar. And then also we're going to extract numbers. We need to know that 2 is a number of people rather than time in the afternoon, for example. And the way that we approach this model is by training, approach this task is by training a CRF on top of the ConverT model. So now, since ConverT is effectively a transformer before it gets reduced down to fixed dimensional vectors, we take those conversationally trained contextual word embeddings and then add a few layers on top, so a few purple layers on top. So we're adding a CNN and then a CRF, a conditional random field, that allows us to tag the input words. So here, for example, we want to extract the number 2. It is marked as the beginning of a span, and then the next token, please, is marked as after. So that would be the way that we would encode that 2 was the correct value to extract from that sentence. And so like another picture of that is we're going to take the contextual subword embeddings, we're going to run them through a CNN just to get a little bit more modeling of the nearby words or tokens, and then output scores for a CRF decoding. So here we would get SpongeBob as the detected value in this sentence. And you'll see that we're doing like subwords so that we're able to deal with any type of span and not worry about out of vocabulary stuff. In terms of an evaluation, it's basically a similar story. So here again, we're looking at using less and less data and seeing how the model performs. We're looking at the F score, precision, like balancing precision and recall. This is on our restaurants data set, which is also released publicly. And again, it's this comparison with BERT, where overall using conversational representations is giving us an improvement over using general language model representations. The model in the middle is to just learn representations from scratch, which is in general worse than both. In particular, ConverT is good in the low data settings. Okay, so this is my summary slide.
There was another question on chat. Maybe you can take that.
Sure.
The question is if you tried recurrent neural network instead of CNN on top of the transformer.
Yeah. I think, no, basically, no, we haven't tried an RNN here. Yeah, I don't know, it would be interesting to try. Another thing is to try an RNN in the actual ConverT model itself, right? Like, still not clear that transformers are always going to be better. I guess in that case, we would be probably have to play a bit with the efficiency of training and stuff. But I'm sure, maybe we would get better results by doing an RNN here. Overall, we find that the CNN plus CRF is giving us pretty good power to be able to represent sequential data.
And question on this comparison versus BERT. I guess beating BERT on the intent classification makes sense, right? Because you have this conversational knowledge embedded in the network, but beating BERT on span detection, where actually this language modeling task seems very useful for that, is against my intuition at least. So do you have any insights on why your model works better here?
Not totally sure. I mean, there's still something about it having conversational knowledge that ought to help slightly, I think. Part of it might just be the similarity of the training domain versus the testing domain, in that Reddit is conversational, and BERT is more likely to be trained on, say, like web pages, documents, that kind of thing. So that might be part of it.
Thank you.
No worries.
Sorry, is in your presentation conversational actually, in your presentation conversational actually equals question answering? It's not a dialogue system. Am I correct, or?
When I've been saying conversational, I've been using it to refer to things like the Reddit data set, and so Reddit is just
yeah,
online.
but is it a multi-round? Is it a multi-round conversation, or is it just a question and answer?
Oh, sorry. Yeah, what the application of these models is in a multi-turn conversation.
Oh, okay.
Yeah.
And the Reddit data set is also, yeah, it's multi-turn. Okay.
Yeah,
Thanks.
it is. But and we've trained kind of versions of this model that take into account earlier context beyond just the most recent thing that was said. But we find that doing non-contextual kind of value extraction and intent detection just works fine. I guess it's easier to kind of go out of scope or out of domain from how the model was trained versus how it's tested if you take into account too much of prior history. But yeah, the application here is things like restaurant booking, where someone calls up and there's a multi-turn conversation to figure out when they want to book a table, under what name, and they might want to ask if dogs are allowed, blah, blah, blah. And eventually they book a table.
And do you also, is this model also fit, or is this something that you do that you also kind of cover the introduction to the conversation before the questions? You know, like the sort of prefaces like, hello, my name is, or such stuff.
Yeah, so what we're doing here is, I guess, like very rigid conversational stuff. So we're not like generating responses per se. We're rather, this is more about the natural language understanding that we're doing on something a user has said during a conversation to extract like the intents, like the categories and the values.
Okay, so in terms of prior history, you don't count in the preface of the conversation. So something that happens before you get to the intent.
Right. The only way that is incorporated is through the logic of the policy, which is the system itself, like the flow chart that we built, basically.
Okay.
Although it is like I was saying before, like it's totally possible to train these models to take into account prior history. Yeah.
Thanks. Thank you very much.
Yeah, no worries. Cool. So yeah, this is ConveRT is specifically designed with conversational tasks in mind, and hopefully sort of shown some evidence that helps with the conversational tasks we apply it to. It gives us competitive NLU accuracies. And also something that I didn't talk about too much is that this type of dot product style response selection can actually power a different kind of type of dialogue where you can basically boil it down to a search problem. You know, if you have the perfect response selection machine, then you can just have a bank of different sentences you might want to say and search through them. Or you might be in the case where you have like documents that are relevant, that kind of thing. And then you can kind of instantly have this conversational aware, conversational search type thing that's very easy to build almost straight out of the box with little like labeled data required, because all it does is kind of have an idea of what response goes with what input. Yeah, that's my talk. So thank you very much for your attention, for letting me talk here. Yeah, that's it. Thank you.
Cool. Thanks, Matt, for talk. It looks like we're going to have at least 50 minutes. There's plenty of room for all the questions you guys have, so feel free to start asking.
Hey, Matt. So thanks for the talk. I was wondering about that slide that you showed that shows the history of accuracy of your model and the exciting part when you switch to transformer from bag of words. I was wondering, are there any other sort of parts of non-neural network stuff that you're still using that you still haven't switched from because they're just working good enough, or there's no counterpart?
So you mean like in our general technology stack, like,
yeah, like
where do we not have neural networks applied? Yeah. So one big thing, I guess, is in the decision making of the dialogue system, which I didn't talk about at all, really. I talked mainly about language understanding, which is kind of an easy or machine learnable part, because there's a kind of obvious input output that we would expect. Like, it does take some work to define what the intents should be and what the slot values ought to be. But once you have that, you can basically just throw neural networks at it, and it's data. It will learn the data. On the other hand, the decision-making part is more hard. Is more difficult to machine learn. So, like, say you've got a restaurant booking system. The way that we build that now is basically with a lot of engineering, or like sort of expert engineering to like figure out what they should say next. And do you like reinforcement learning is just like not really going to work. And then what if we have a new feature that we want to implement? Like, we want to tell them that, oh, hey, it's Christmas is coming up. Do you want that's not really a machine learnable thing. That's more of like a product feature we got to get in there. But maybe there's some kind of fusion of response selection with the more rigid, essentially like flowchart style development. Like, we have this model that can rank responses. Can that take some of the weight off of the policy or decision making part? Yeah.
Okay, cool. And how do you handle a situation where your model gets confused about the question and you would like to escalate it to human, or do you handle that case somehow?
Yeah, we have that like very much built in. A lot of it, I guess, is kind of confidence thresholding and simple rules like detecting loops, right? Like, we have some idea of if progress has been made in the dialogue, and if they're stuck at the same bit for 3 turns, for example, we would just say, oh, sorry, I'm going to forward you to one of my human colleagues, and it goes to a real person. Yeah.
Okay. But, and there was a question about using recurrent neural networks, and I was something caught my attention. If you could unpack it a little bit, you're still not sure that transformer is actually better for that, and it could be interesting to try out recurrent, leaving aside the question of sequential and versus parallel and all the training constraints. What's your intuition here? Like, where could RNN, say LSTM, beat transformer?
Yeah, I think one of the tricky things is that this pre-training task is actually not super discriminative at this kind of sequential level, I think, because you can get a lot of the way by just doing kind of simple topic matching. If you imagine taking a sentence from Reddit or any discussion forum and then a totally random response, then the amount of understanding you have to do to realize that these are probably not from the same discussion is not that sophisticated, which kind of goes against why I'm saying that this is a good pre-training task. But actually, like, you can get a very like good baseline just by doing simple topic matching. But If you have enough negative examples in the training, then you will start to get some difficult discrimination that the model has to do. So maybe in those cases of where you're testing the model, I don't have any idea of like if an RNN would be able to do inherently better if, you know, given as much computation time as needed for training. My feeling is that it would probably only help in the smaller data set condition, because it kind of embeds that sequential bias into it. And that possibly with enough data, a transformer could learn anything. So yeah, it might be a function of how much data you have. So maybe if you're talking about training in Polish, for example, right? You don't have there's no Polish Reddit at that scale anyway, right? Yep. So maybe you'd want to be doing recurrent models on a conversational data set that you could find in a language with fewer resources.
Cool, thanks.
I have a question. I'm not sure if my connection quality is good enough, but
I can hear you.
Oh, sounds great. So my question is rather, I have two questions. One is more naive, and the other one may be a little bit too high level, but let me give it a try. The naive question is, are you open sourcing those models? And the second question is, you said that there is still a need for a human, like a human-based team for this request ingestion. So how scalable are those systems eventually? So as I said, it's slightly more high level, so you don't have to be very specific in that one.
Yeah.
Thank you.
Are we open sourcing our models? Yeah, ConverT is actually available to use as a TensorFlow hub module. So we share the pre-trained model. We're not sharing the pre-training scripts and stuff. But if you have an application in English that you want to try using these features and train a small network on top, then it's very easy to do. So if you look at PolyAI's GitHub repo, you should find it. So you asked about how our systems need a human in the end a lot of the time. Are you referring to the case where like the system, like I was talking about, where the system hasn't made progress and then it eventually needs to pass on to a human colleague? Is that what you mean?
Yeah, exactly. Like because at the end of the day, it needs to be used by humans, and basically each and every client, they have their specific needs. They have their like environment changing, for whatever reasons. They always needs to change, adjust, and adapt the product to themselves. So like from what you said, I understand that the AI is pretty much great in doing stuff, but not necessarily that smart when it comes to handling those more nuanced requests.
Yeah, I suppose without like solving artificial general intelligence, you're always going to have some calls that this machine can't handle. Like we're answering calls for a restaurant, and someone calls up saying, I've got a delivery of toilet paper for the restaurant. Like how are we supposed to deal with that without having like solved AI?
It's a real case scenario.
Yeah, it happened, or something like that happened, right?
And are you using the actual conversations as a training to improve your model?
Yeah.
And how do you evaluate that, okay, it went well or it didn't go so well? So I'm thinking about the situation where the customer asks a question, the model replies, and then you want to use that as a next iteration to improve the system. How would you know whether it went well or not?
Yeah, this is a recurring, like, difficult issue that we have, and I think something that there must be like a genius idea that we've missed, or that the field has missed in general. But yeah, if you might be able to tell that something went wrong, but how do you know where it went wrong? Especially in a multi-turn conversation, that it could be something early on, and a few turns later they eventually hung up. The best that we have now is basically to listen to the calls and to annotate them of like, okay, actually speech recognition was bad here, you know, that kind of thing, or the NLU detected the wrong intent. Yeah, it seems like there ought to be some kind of self-learning that should be possible due to the interactive nature of the system. So like the system itself could gain confidence about something it said earlier, you know, by asking a question to the user, for example. You don't do a lot of that, but you know, maybe that would help us scale, for example. Yeah.
Or like a keyword when you are going into like a super user mode, when you are telling AI what to actually do.
Yeah, like an expert talking to the system and like teaching it as they talk to it. That would be cool.
I was wondering about like a distant supervision type of approach, where maybe you have something that you know is okay, and you could use it to teach your model. Like you have some good examples to look for this type of patterns. I don't know. It's just I'm in a slightly different area. The conversational search is actually what is mostly interesting for me, and then there I think it's slightly easier because the data is sort of better structured sometimes. But I think you have more general problem here.
Yeah, I love like the academic stuff will highly structure the dialogue data sets. You know, here's the ontology, here's what they can talk about, and then when you have a commercial system, then people will start talking to it and they'll do something totally different that you never anticipated. And if you compare that to academic data sets, which can be built using Mechanical Turk, where you've told the user what to say, you basically don't get any of that behavior, which is a big kind of like recurring theme for us.
And how much compromise do you have to make to get it running in production as a commercial product? So to meet some latency budget, for instance.
So we haven't really hit that much issues with running this ConverT model. I think, you know, partly because, as I said, like we had sort of resource constrained at training time and at iteration time. So we didn't actually have to do anything that special. It just runs on CPU.
Okay.
Yeah. Maybe we could, you know, if we upped those requirements, we could say, oh, it's a couple of years later or something, it's cheaper, we got better GPUs. Maybe then we would end up with a model that we would have trouble productionizing. I don't know.
Matt, as a recurring problem that we are, you know, experiencing for like Polish application is the fact that most of the models are trained in English ConverT as well, right? Could you like comment, how would you approach the problem of, let's say, taking model like ConverT and apply for a conversation AI in Polish? Any tips?
I mentioned the universal sentence encoder before, which is actually a pretty similar model. It's another kind of dual encoder .product thing. This past year, they released a multilingual version of that model, which would be worth trying if you're just, you know, trying to check out how things work on your application in Polish. The way that they trained that was to translate Reddit into 16 different languages using Google Translate. You know, being at Google, like that wasn't a prohibitively expensive thing for them to do, or maybe it was, but no one told them. For us to translate all of Reddit into like 16 different languages would be like millions of pounds or something. And it also sounds kind of not satisfactory, right? Like, oh, we're just going to translate this English data set through some noisy automatic machine translation. But it kind of implies that they tried a whole bunch of things and then that's the best thing that they found. The ideal situation is that there is a Polish Reddit, but there won't be something with like 3.7 billion comments, I assume. It's basically an open problem.
I think it's the problem with Polish is that there are some, you know, corpora, but there aren't that many with sort of the real colloquial language people are using. There are things like from Parliament and that stuff, but nobody really talks like that in a chat conversation. So
yeah. Pavel, what do you think about the translation idea?
So like, I guess we can, comment that we actually, for different languages, we're playing around with the live translation of like Google APIs for any, and actually combining with the original translation into English and translation to original with UV works quite okay. It's not as good as data for pure English, but I think we're reaching the level that is good enough for production. So that would be the first step when you want to deploy something in Polish.
Cool. How are we doing for time? Oh, is it Vicop? Is that a social networking, Polish social networking?
I guess it's Polish. It's a Polish website. Totally. Yeah. Yeah. You can look at it as a Reddit or some sense.
Yeah. You should crawl that type of website.
Yeah, exactly. The problem with I don't know what Vicop, but like the big thing for Reddit is that somebody was crawling for a couple of months, I think, right? Reddit, and then publicly shared the data. I'm not sure if that's going to be that trivial for any other website. So
yeah, that's the nice thing about Reddit is it's not a crawl. It's just the company shares their internal database. Yeah,
it's probably against the rules of Vicop to do something like this, I would imagine.
Yeah.
Cool. Any other questions?
No question, but thanks a lot, Matt, for the presentation and joining us. It was great learning and great opportunity to have you join our meetup. Appreciate it.
Cool. Thanks, Derek. And good to meet you and everyone else.
Thanks, everyone. Thanks for joining.
I believe, right? Yeah.
Thank you.
Thanks. Great.
Thank you.